Uh, Hello everyone. I'm Jaogen a postdoc in ICTS, Seoul. Today I talk about the information engine. They are collaborated with this work. So this is a typical heat engine extracting work from the heat flow. The heat flow from hot reservoir to cold reservoir. So, however, in the information engine, usually there is one single reservoir, like this. So, yeah, here I have a box and containing particle, and it is thermally connected to heat bath having temperature T. How we get work from this device? At certain time, I insert the bar here in the middle of the box. Then the probability for finding the particle on right, left on or on right is equal to 1/2. Yeah. So I got the position this position with probability 1/2. Then I put the load. I put the load here. So this bar is allowed to move. Then, yeah, I can get work from this device. So, yeah, obviously, heat is also produced in the reservoir. In the quasi-static limit, I can exactly work and heat, and the work and heat is given by log 2, and this is a well-known Gillard engine. There was some controversy about the thermodynamic second law problem, because if you consider cyclic engine, then for one cycle, the entropy production is just given by the heat here, but heat is negative, so yeah, it seems to violate the thermodynamic second law, but it's not true. You never forget this demon, doing measurement and feedback on the system. If we consider the composite system of this engine and memories of demon, then you can see thermodynamic second law can be remedied. Let's go more detail. Gillard engine has two states, left or right state. So the memory storing the measurement outcome is also two state, right? So these are possible configurations, just four. After the measurement, we can get this distribution because during measurement, memory copies the system state. So they are perfectly correlated. That so in this time, the distribution is given by this form. At the feedback, this correlation is decreased. So at the end of feedback and relaxation process, the correlation is completely gone. So we can get the uniform probability distribution here. So in this picture, obviously the composite system entropy is increased. So if you calculate the Shannon entropy at the beginning and at the end of process, then you can immediately see the change is log 2. So using this Shannon entropy change and heat, we can get the thermodynamic second law. So this kind of thing, the total entropy composed of the Shannon entropy change plus heat satisfy the thermodynamic second law. Yeah, this is what Saga and Ueda did several years ago. If we want cyclic engine, then you should consider measurement process now, right? During the feedback and relaxation, the correlation or mutual information between system and demon is decreased so that the entropy of the composite system is increased. So you can expect the opposite situation in the measurement process in order to make this cyclic, right? So it means that during measurement, the mutual information between the system and memory increased so that the composite system entropy decreased. So basically, this is an irreversible process. So we need something here. long time ago, Landau suggests the memory resetting process to solve this thermodynamic problem. In his process, the memory resetting is also irreversible process, but he assumed the memory is surrounded by heat bath. So heat can be dissipated like a usual stochastic process, so that's okay. After resetting, the measurement process can be reversible without any change of the entropy. So due to the Landau process, thermodynamics becomes fine, but still we don't have any information about energetic cost for the measurement. So in our work, I devised some stochastic measurement by putting the additional reservoir here. So this stochastic measurement, information engine can be regarded as two heat-bath engine, where we can count the full energetics, right? So it quite similar to the Landau resetting process, yeah, because this is also stochastic, but our measurement process is just a single-step process without any memory resetting. So by doing making the stochastic measurement, we can calculate the efficiency in the end. So yeah, this is that's my motive goal of this work. So to study the stochastic measurement, I consider the simplest two-state model. So our model has the two energy level here in system and one single bit memory. So the probability distribution can be defined as the four-component vector here. So let me first discuss the relaxation of the system. The relaxation of system is just the relaxation process within the reservoir. It's just ordinary relaxation process. So we can define the transition rate given by Boltzmann weight. So using this parameter Q, we can construct 4x4 transition matrix. This is a usual process for the usual stochastic process. So we can calculate whatever heat or the shadow entropy using this transition matrix. After the relaxation, measurement is coming, but here I just assume measurement was done. Okay, I discuss measurement process later. So here I consider the general measurement. So there are some error in measurement process. So it means I can get some incorrect measurement outcome with this probability at epsilon. Now the feedback device, whatever demon, take a look at the memory state. So not system state, only memory state. So the device finds zero state in memory, then nothing happens. But the memory state is 1, then the feedback device change the system state. In this case, this particle going down to ground state, losing its energy. The energy loss becomes the work extraction here. This feedback process can be described the reversible dynamics, reversible matrix. So I assume this reversible feedback can happen suddenly, so I don't need here the time. Okay, measurement is a copying process of memory, right? So to implement the copying process, I consider the same two-state model on the memory. But each ground state is depending on the system configuration. So in this case, yeah, the ground state of memory is 1 because system configuration is 1. So I put the another hidden reservoir here and set the transition rate as epsilon. Then, yeah, the epsilon and energy gap, and temperature should satisfy this Boltzmann weight. So this is become just by doing this, and the measurement process becomes just relaxation of memory, right? Just usual relaxation dynamics. So we can construct the usual stochastic matrix for relaxation like this. So the very similar way in the relaxation of dynamic system. So if you look at this matrix and take the infinite time limit, then immediately you can see that the measurement outcome with some probability. So if you consider the finite time measurement, then maybe you gain additional noise on this measurement process. Anyway, the important thing is that to operate the measurement device, we have to apply the potential because we need this energy gap between the memory state. So it means we have to apply the work supply here before the measurement, and this is ordinary stochastic process. So of course there are some heat dissipation. Now you can see that this information engine model becomes two heat-based engines. One heat-based is associated with the relaxation of system, and another one is for the memory relaxation, right? So let me show you some result about this model. So after many cycles, then this model arrives in the cyclic steady state. It means that these two guys are same, right? So this is cyclic condition, cyclic state, and also the measurement process doesn't affect the system energy. So we can see immediately this kind of energy conservation. The energy, the work supply for the measurement device should be totally dissipated to the heat reservoir by the heat, right? And also the system is in cyclic steady state. So another energy conservation is coming. The heat, the work extraction by the feedback should be same with the heat flow from the reservoir to the system during the relaxation. So this is the energy conservation loss. And let's discuss the thermodynamic second law of this system. So at each time, I can calculate the Shannon entropy of the composite system. So, and the relaxation and measurement is here are just ordinary stochastic process. So I can tell the entropy, Shannon entropy change plus heat satisfy the thermodynamic second law, right? There are no something strange. So here, this is the thermodynamic second law for the relaxation process. This is the second law for the measurement process. Since I used the reversible process for the feedback process, reversible feedback, so there is not the entropy not changed during feedback process. So under the cyclic condition, we can see immediately this guy should be same with the Shannon entropy change during the measurement with different sign. So putting them together, we can get these inequalities. This equality is nothing but just thermodynamic second law of the ordinary heat engine, right? And putting them slightly different way, then we can see another inequalities. So under the cyclic condition, I can rewrite this inequality in terms of work and the mutual information developed by the measurement. So it said that each work is bounded by the same mutual information, but opposite way, opposite direction. So if you have same temperature here, then you never get positive net work because the work supply is already larger than the work extraction. But if you change the temperature, then maybe you get positive work. This is my calculation here. The forget about other curves. Only look at this. This blue curve is the work extraction, and this orange curve is work supply when I supply the temperature difference like this one. Then you can see immediately here work extraction is larger than work supply. If we define the network like this, then yeah, obviously in this region the network is positive. It means that here our information engine works as an engine. So I want to calculate efficiency of there. By information engine now just the simple heat engine. So we can define the efficiency in usual way like this. The network divided by the input heat. Then you can see that this efficiency should be bounded by current efficiency because our model satisfies this second law, right?
Sorry, in your previous slide, what was that in the x-axis?
X-axis is just sorry. This axis is a parameter for the system relaxation. So if the Q is close to 0.5, then it means that their gap is very small. And Q goes to zero limit, then the gap is infinite or temperature or infinite, whatever thing. If I fix the temperature, it means that just the gap. Okay? Okay. So yeah. So okay. So my efficiency should be bounded by current efficiency. So I want to check this inequality by the direct calculation. So my model is very simple. So I can get some exact expression for the efficiency. So this lambda is given by this form, and this guy has also this form, and this guy is also this form. Anyway, so I can get exact expression, and from this, I found the lambda is always larger than 2. And this equality can be achieved in the infinite time limit. It means that the efficiency is maximum when we take the infinite time limit, and this is always smaller than the current efficiency. This is obvious because our engine never be quasi-static limit even in the infinite time limit. So my model cannot get this current efficiency. Yeah, this is my last slide. Infinite time operation, infinite time engine is non-realistic, right? So practically, you should consider efficiency and maximum power. This is the efficiency curve, and this is the power curve in function of the time. The tau is the operation time. So you can see that infinite time here, the efficiency is maximum, but the power goes to 0. The power is maximum here. So I can calculate the efficiency at this point. Eta maximum is very small, then I can expand this eta O in terms of the eta maximum like this. So you can see immediately some difference from the usual heat engine, because the usual heat engine has the 1/2 coefficient here, but I have 1. I don't know why now. I'm still studying about this. Okay, this is my summary. I have investigated the information assist heat engine, and I found some thermodynamic second relation, and the efficiency is different from the usual heat engine. Thank you.
Thank you.
After the feedback, what do you mean by correlation has been lost?
Because
Your measurement established
yeah.
correlation between
Right. Yeah, because there are some. Yeah. Okay. First of all, the thermal fluctuation during the relaxation process make the correlation weak. The memory is not changed during the feedback and relaxation process. Only system is changed during the process. So thermal fluctuation of the system make the correlation between memory and system weak. Because memory is just fixed.
Your memory device that determines the evolution of the system.
Sorry, what?
So what has been stored in the memory device that will determine the dynamics.
I just assume the bipartite system. Memory, it means that during the system dynamics, I want memory is fixed, and during the memory dynamics, I want fix the system state. I assume the ideal bipartite system.